Hello, welcome to Stars, Cells, and God. I'm Jeff Zweerink, a PhD in astrophysics, joined by Dr. Hugh Ross, also a PhD in astrophysics. And we're going to be talking about the largest organism in the world and one of the most unusual physical constants in the world. Hugh, good to have you here today. I will just throw the ball over into your court because you're talking about the largest organism in the world, which I would say is a whale, but I think you're going to surprise us.
Yeah, it's actually a plant species.
A plant? Oh, that's so much more boring.
Well, you've probably been hiking in mountain areas. I enjoy doing that. And particularly here in the United States, when you get up to higher altitudes, you see these aspen forests.
Mm-hmm.
And we actually have a slide here that people can look at. And every tree you see here is part of a single organism. It may be a good analogy. Think of strawberries. When you plant strawberries, what does a strawberry do? It sends out little stems along the ground where a new strawberry plant happens. That also takes place with a quaking aspen. You get a single seed that gets into the ground and it puts up a tree, but it also sends out roots underground, and then a new tree comes up.
So this is something different than like a birch tree or a pine tree, that's just a single tree in the yard. The aspens are actually all physically connected underground then.
Yeah, and you can think of it as clones. What's happening is you get this little stem coming up with all the leaves and branches on it.
Right.
But then it sends out these little things underground, and then a new tree comes up, and it's basically a clone of the original.
That's kind of like banyan trees have that same sort of property, don't they?
Well, banyans will send up, but they're all kind of like in one area.
Okay.
So, but there are several trees that do this. And, we've said here at Reasons to Believe that the oldest tree in the world is like an hour's drive from the Reasons to Believe headquarters.
Okay.
It's in a suburb of Riverside.
I think I've driven by that tree. So.
Yeah. And it's like 13,500 years old. But it's a clone in the sense that you get a mother tree that produces daughter trees. And in the case of the one in, Rubidoux, California, you can actually look at all the tree rings and you get a record of the past 13,500 years because you can see.
Presumably, is the mother tree still there?
Well, the mother tree is dead.
Okay, that's what I'm thinking.
But the rings are still there.
The rings are still there.
So you can actually trace all the way back.
Okay, sorry. Just how can the rings still be there if the tree is dead? That part of the tree is dead. Well, can you see the mother tree that's fallen down? I presume it's decayed away or something.
I've not actually been to the site.
Okay.
I just read papers on it.
Okay, very good.
But even though the particular stem is dead, the rings are still intact.
Very good. Okay.
Yeah. So this is a situation where the stems really don't last that long. Typically, with quaking aspens, the particular stem will last a few centuries, and then it dies.
Right.
But there's always these new stems coming up.
Right.
And so you see this prolific forest. So like in the picture I just showed there, the stems will change with respect to time, but it's still a very dense, bunch of aspen.
So like with the banyan tree, that's kind of like the size of a house. It spreads out over something like that. How large of an area does an aspen tree spread out in that
Well,
sense?
this particular organism extends over 106 acres.
106 acres.
Yeah, that's 43 hectares. Or 106.
Well, that's a useless measurement. Well, I don't know what a hectare is. So, how does a acre? What's the?
A hectare is 100 meters by 100 meters.
Okay, all right, okay.
An acre, I think, is like 200 feet by 200 feet. It's 200 something.
Okay.
So it's like 2.5 acres or 2.4 acres makes 1 hectare.
Gotcha.
But you're probably more familiar with acres. 105 acres is a really large area.
Yeah.
And that's all one organism.
Right.
So, and they counted 47,000 stems in this single organism.
Okay.
And, we would look at it and say, that's 47,000 separate trees. But they're actually all part of a single organism.
There's this part of that's got a really cool wow factor. That's just cool. So.
Well, I like walking in these aspen forests because it just realized here I am surrounded by hundreds of trees, but they're all one single
Yeah,
organism.
that's pretty cool.
Yeah, it really is cool. Well, a team of ecologists and biologists and the geneticists went to it's in Utah. It's near the Fish Lake area of Utah. It's around 8,000 feet elevation. So they went there to study this, because they were kind of saying, hey, this is the biggest organism. Let's actually do a genetic study on it. And so they took 500 samples from the leaves, the bark, and the roots. And when they say bark, they mean the stem. Okay?
Right.
So you got what looks like a single tree. They took a sample there. They take a sample from the roots that are underground that are making new stems. And then they took samples of the leaves. And then they did a genetic analysis on them. And what they discovered is that this particular organism produces a lot of somatic mutations. And that term somatic means it's a mutation that's taking place in a cell that plays no role in reproduction.
Okay.
And so, there's a mutation there. It's not going to be passed on through any kind of sexual transmission. So it'd be like, a cell happening, a mutation happening in a cell in your skin. That's not going to be passed on to your children.
Right.
So, and what they discovered is there's a whole lot more in the leaves than there are the stems and the bark, which is kind of a good thing for the organism because the leaves don't last long.
Right.
A year, they're gone. And so you can tolerate a lot more mutations in the leaves than you can the bark and the stem, which are going to need to leave a long time. But they found 4,000 genetic variations in the 500 samples they took, which means this is producing a lot of somatic mutations. And they said, well, of course, the organism is a triploid. Now, we're diploid, which means that when you look inside of our cells, we have chromosome pairs. In the case of this quaking aspen, you don't have chromosome pairs, you got sets of 3.
Okay.
And so, where you got 3 chromosomes making up a set, that gives a lot more opportunity for somatic mutations to occur.
So why is that? Because I would think the more chromosome sets, or the more numbers in the chromosome, the more opportunity you have to have mutations that will be passed on as well. Because you got to get the 3 chromosomes from somewhere, correct?
Well, okay. It's like, I think we have, 47 sets of chromosomes, 46? But they're all double. There's 2 chromosomes that make up each. This is different.
Right.
Where you got the 3s that make up the different patterns. And where you got 3, you could have a mutation in one as opposed to the other. So when you got 3, you got more opportunities for these things to take place.
Right. No, that makes sense.
That's just
the more number, the more
the
mutations.
more number, the more mutations. And so they said this actually helps the species to adapt. And so, and what they noticed is that in the lake, they did a sediment core. And what they found is right next to this 106-acre organism. And they noticed that there was pollen that went down 60,000 years.
Okay.
So this gave them a clue. This organism has been alive for a long time. And
they presumably they can trace the pollen to that aspen tree as well, or the aspen grove as well.
Well, it's aspen pollen, and the only organism around to provide it. Because the sediment core is right next to where this organism was living.
That makes sense.
So they just presume, okay, this pollen comes from the organism, and the sediment core tells us that the pollen's been deposited over a 60,000-year period. Now, they were able to say that we can prove that for the last 15,000 years, the pollen's been deposited literally every year. For 60,000 years, pollen's been deposited, but they don't have a complete enough record to prove that it's been continuous. It looks like it's continuous, but they said we can only prove it definitively for the first 15,000 years.
So, and presumably, are they finding layers in the sediments that
That's
that they're yearly layers that they can count up? So this is, Yeah, not the subject of what you're talking about, but another piece of evidence that the Earth is older than 10,000 years, because we've got a direct record here that would put it much older than
Yeah,
that. So.
I mean, it's just like ice cores, sediment cores give you a record of what's been happening in the past history of the Earth.
Right.
So, but then they said, okay, we know that the last ice age had way greater climate instability issues than what we're experiencing right now. And it says it looks like these somatic mutations are allowing the organism to adapt to the changing environmental case. So then they came up with a mathematical model saying, okay, let's look at the somatic mutations that we can prove took place. And they're able to do that to come up with a minimum age for the organism.
Okay.
Came to 16,000 years.
Okay.
Now that's significant because that breaks the record. The oldest tree that we can prove is this one in Rubidoux, California, 13,500 years. Here we got one that's 16,000. And then they said, okay, that's the most conservative estimate. Now, if we look at what we think is the maximum number of mutations that took place, then we get an age of 81,000 years.
Okay.
Minimum, 16,000, but the maximum estimate for the number of somatic mutations would have allowed it to live for 81,000 years. And they said what's probable is 34,000. So they're basically saying we think the best estimate for the age of the organism is 34,000 years. Minimum age 16,000, maximum age 81,000. And that's assuming that there aren't any other mutations we're overlooking. And so
there's a disconnect that maybe you can help me with. So when they were looking at the sediment core, they find pollen dating back 60-ish thousand years.
Right.
So that would seem to argue that this organism has been around for 60,000 years. Now you're saying, so what is the just if you could explain it again, what is the dating that, or what technique, what are they using to get the date of saying it's got to be at least 16,000, maybe 80,000, and probably 34? It's not the sediment cores, correct?
No, what they're looking at are the somatic mutations.
Okay.
Basically saying, okay, these somatic mutations are indicating that mutations are happening at a particular rate to deal with the changes that are taking place in this environment. And the estimate is basically, okay, how many somatic mutations that we know for sure have happened that enabled the species to adapt. And on that basis, they develop a minimum age for the species.
Okay, so they're looking across all of the different sprouts that are coming up,
500
saying
samples.
we can measure all of the mutations in here.
Right.
How many of these had to be true or how many of these were something that a new tree came or a new sprout came along, and in some sense measuring how fast would these accumulate, or how fast would it take. What's the minimum amount of time it would take to accumulate this amount of mutations?
Right.
The minimum is 16, the maximum is 81, most likely is 34.
34.
Okay, all right.
And they kind of use the sediment core as a way to, check, hey, this basically shows that we're getting a consistent picture.
Okay.
So it's two independent methods. They're using a genetic method to come up with an age. They're using a sediment core, and they're saying it's about the same. Because the sediment core was saying it's at least 15,000 because we've got a continuous record.
Okay.
The genetic analysis is saying at least 16,000. So those numbers are very close.
Right.
That's the most conservative estimate. And then they're saying, but hey, it's more likely older than that. In fact, people have commented, you've only taken 500 samples. If you took more samples, you might discover, because what's happening is a somatic mutation, say in one stem, may only be present in that stem. All the other stems may not have it.
So unless you sampled all 47,000, you're not going to get the actual number of mutations.
and that's
it would
where
take that sort of analysis.
Yeah, and they kind of made an estimate as to how many mutations they're missing.
Right.
And so that's where they came up with the 81,000 years.
Gotcha.
But other people who've read the paper said, it could actually be 200,000, maybe even 300,000. Because, and that's how they ended the paper, saying, okay, we're basically showing this is a legitimate technique. There's rationale for going there and saying, let's do a much more extensive genetic analysis. but this is what we've discovered so far.
So it's if I remember or the statement you made earlier, they've got the sediment core goes back 60,000 years, and they've got pollen all through that. They can clearly count up to 15,000 years, but there's pollen that I thought you said that the pollen was throughout that record all the way back to 61,000. Am I missing something? Okay.
What they're saying is we can prove the continuous record for the first 15,000 years.
Okay.
As you go deeper into the sediment core, the picture isn't as clear. And so they said we have to admit there's a possibility that from 15 to 60, it's not strictly continuous.
Okay.
It may be. We think it is, but we can't prove it.
Okay. So it could very well be that there's, I was just trying to think, how do you get pollen in the 60,000-year-old sediment from an aspen that only has been around for 34,000 years? Could you conceivably have one aspen that grows for a while and then another one, when it dies, a new one takes its place, or is that not how it works?
Well, that's what they're saying. They don't think that's likely because it's a rather extreme situation where
right.
the organism completely dies and then a new quaking aspen organism takes over. So they're basically being very conservative. What they're saying is that most likely this single organism has been here for 60,000 years. We can only prove for certain 16. And if you look at the sediment core, we got a continuous record we know is continuous for 15,000.
Right, okay.
There's possibilities that it may not be continuous all the way back to 60, but for most of the 60, they're seeing pollen.
Right. Okay, so it is a sort of thing that there's an interesting part of this future study of this thing could conceivably 60, 70,000 years old. More data, better analysis techniques, whatever, might actually allow both the sediment and there's improvements you can make in the sediment record and in the mutation record that might resolve this. How old is it? But both of them are saying it's at least 15 to 16,000 years old or older.
And what caught my attention, they didn't really mention anything about the ice core records. But, in looking at ice core records, it's clear that during the last ice age, especially from, say, about 18,000 years ago to 80,000 years ago, you see extreme climate instability and rapid changing in the climate. I mean, you see this in my book, Weathering Climate Change, where during that era, you got the global mean temperature jumping up and down by 10 degrees centigrade, 18 degrees Fahrenheit, on time scales of a millennium or less. And that's extremely difficult for forests to withstand.
Right.
And it's like, okay, fir trees and hemlocks aren't going to be able to survive those kinds of conditions, but this quaking aspen with these somatic mutations would have the capability of quickly adapting to these radical climate changes.
So you're going to have some of the sprouts that may or may not survive, but other mutations
will,
and some
because
will
mutations have enabled them to.
Yeah, good. Now, I was just curious. I know that during the last ice age, glaciers advanced quite deeply into North America and even into the United States. I'm gathering that where this aspen tree is, or aspen organism is south of where the glaciers advanced to, because I'm assuming glaciers would wipe it out if it was covered in glaciers.
Yes, and they actually did address that in the paper, saying we're looking at Utah, which is fairly far south.
Fair.
But this is high altitude, and the last ice age, that made a big difference.
Right.
But what they basically were able to demonstrate, this particular organism is just south of where you got really thick ice sheets periodically coming down. And that's what was happening in North America. You get these thick ice sheets moving south, moving north.
Right.
And this is happening quite rapidly, but it's at a low enough elevation where, yes, it is being impacted by a lot of ice and snow, but not thick ice sheets.
Gotcha.
Which means it would have the possibility of surviving, but it would only have the possibility of surviving if it had great adaptability.
Right.
And these somatic mutations enable the species to adapt. As you pointed out, some stems will get wiped out where they don't have the mutations, but others will survive. If you got 47,000 stems and you got these somatic mutations occurring, you got a reasonable probability that, say, a few dozen stems will survive even a really dramatic climatic change event.
Right.
So, and we have some evidence that this must be the case because we know that other species dependent on these aspen forests survived. You know, like deer, for example, will feed on these aspens.
Right. Okay.
And so the fact that they survived means something must have been keeping these quaking aspens alive, so the species dependent upon them could also be kept alive.
So it sounds like the another utility of studying these quaking aspens is that they're a more fundamental part of the ecosystem. It's not like they're just one of a bunch of trees that are in there. They serve a little bit more.
Well, you've probably heard the term
outspoken role.
keystone species,
Okay.
which is a species that's crucial for the survival of many other species. You know, like beavers are a keystone species.
Right.
Honeybees are a keystone species. If you take them away, a lot of other species wind up going extinct. And these quaking aspen are in the same category.
Gotcha.
A lot of species are dependent upon them. But what attracted me about the paper, and this isn't mentioned in the paper, is that this is an incredible design feature that our creator created these organisms that are triploid, that have the capability of producing all these clones so they could actually survive these dramatic, climatic change events. And as I've written in Weathering Climate Change, the severity of the last ice age actually plays a huge contribution in enabling human civilization to get the population and the technology we have today. So it's like the creator knowing, hey, I don't want billions of human beings because I want to redeem a whole bunch of people, and I want them to have the technological capability of being able to have a large population and to communicate the gospel message. Well, if that's the case, we need to have this severe ice age that precedes this era of a large human population, and we need lots of species to be able to survive under those conditions.
So flesh out. I mean, what are? I mean, there's just kind of cool as an organism. This aspen, quaking aspen grove, or whatever you want to do.
Well, it's cool that it's so big and
no,
so old.
I agree. Yeah, but you know, you're saying there's a design feature in this. I mean, kind of flesh that out. What are the apologetic takeaways or the implications of that? I guess in a little more detail, how would you describe that?
Yeah, to be brief, it's like, okay, in order for billions of us humans to exist, we do need to be in an ice age cycle. You know, that's the main theme of weathering climate change. And in order for us to have a large human population during an interglacial, where we have the technology to take the good news of salvation to all the people groups of the world in a relatively short period of time, we need the ice age that precedes us to be particularly severe. With a lot of climate instability.
Yeah, so what is it about, I mean, if I'm getting what you're saying, the fact that you have ice ages, or rather the remnants of the ice age is what allows or provides something during the interglacial that allows humans to, what is it that?
This is all covered in Weathering Climate Change. I list like about 15 or 16 benefits we get from being alive presently with an ice age that looks like the last ice age that we have. But a couple of examples, okay? The last ice age covered 23% of the planet, and it was really thick ice.
Right.
A lot of that ice is still here. And the melting of that ice feeds the major rivers of the world.
Right, okay.
It happens here in North America. It's especially dramatic in Asia because you've got the third pole, the Tibetan Plateau, which is covered with a huge amount of ice. The melting of that ice during the interglacial feeds the major rivers that irrigate the great agricultural plains, which means...
So there's a very real part that to get the amount of water and irrigation of the planet you need, being a long time in an interglacial runs into problems because the waters that feed that will, assuming that's all that happened, they would run out eventually.
Yeah.
And so having that glacial period where you build up these storehouses is key to having the amount of fresh water that we have now.
Yeah.
Okay.
I mean, that ice has been melting for 15,000 years. Well, for that to happen, you need a lot of ice to start with, okay?
That's kind of what I was getting at. Okay, so what's the
wonderful thing about melting ice is that you basically gives you water 12 months of the year.
Right.
Whereas when you get a rainstorm, it flows out into the ocean, and suddenly your soil is dry.
Well, and the worst part out here in California, you only get rain so much of the year. So,
Right.
so you end up with a lot. You end up
Well,
with desert.
like we
desert
here in
otherwise.
California, we are able to grow a lot of food because we have a high mountain range where there's a lot of snow and ice.
Right.
And the melting of that snow and ice means, hey, during the summer months when there's no rain happening, we're still getting water
Right.
from the melting of the snow and ice.
So that's just that amplified on a
That
on a much
amplifies.
longer time scale.
And
with
there's a
the glaciers.
fertilization thing. The fact that the last ice age was as severe as it was, I mean, you had thousands of feet of thickness of ice covering over half of North America, for example. When that ice melts, the continent of North America, and this happened to all the continents, they rebound because you take all that weight of ice off the continental landmass and suddenly
Pops back up.
that
Yeah.
pops back up. And that popping back up effect ignites volcanoes all around the world. And so as the ice was rapidly melting at the end of the last ice age, you had all these volcanic eruptions. Well, volcanoes emit very nutrient-rich dust
Right.
and ash. And that's why people like to, grow things near a volcano because they know they got very rich soil.
But volcanoes are bad because they cause damage, Hugh. I mean, what do you?
Right. But you've probably noticed this. What happens is after a volcanic eruption, all the people left come back. The reason they come back is they know the soil is going to be very
Gotcha.
nutrient rich. And so they're going to be able to grow a lot of food. Well, this was a worldwide event. And also you've got, when the ice melts, it generates winds off of the high plateau that blow nutrient-rich dust and deposits on the low agricultural plains.
Right.
So those are three benefits.
No,
There's a bunch
I
more.
appreciate that. And so there's also a part of that even during the interglacial or during the glacial period, you've got this remarkable organism that's key for helping other creatures survive, especially during a very difficult time, has this adaptability that allows it to survive and allows those other organisms to survive as well.
Right, and I think it even allowed humans during the last ice age to benefit.
You have to explain that one a little more.
Well, I mean, if you've got firewood available during these extreme climate events, that's going to be a benefit.
Gotcha.
And hey, deer feed off of these aspens, and so that means, hey, that's a food supply.
Right.
Because you can get, the hides of the creatures.
Right.
So, and we have good evidence that humans were living during at least a good chunk of the last ice age. And so having organisms that can survive these extreme climate changes would even benefit humans that are alive at that time. So bottom line is genetics is incredibly complicated, but the more we study genetics, the more we see how wonderfully designed it is to enable life to thrive here on planet Earth in the way that God intended.
That's a cool discovery. Any final comments, or is that the wrap up there?
Well, the paper is not yet published.
Okay.
It's in the peer review process, but it's going to come out in the Proceedings of the National Academy of Sciences. It's in the notes that will be posted with the show.
Right.
And the preprint can be read in its entirety right now. But I imagine within a couple of weeks, maybe a month, it'll be published in the Proceedings of the National Academy of Sciences, USA.
Very good. Well, I'm going to shift gears a little bit, and instead of talking about a plant here on Earth, talk about the cosmological constant, or dark energy, space energy density. Goes by various names depending on how what specifically you're talking about. But what I wanted to focus on with that is how everybody recognizes that the value we see for the cosmological constant is unusual. And it's unusual in this way, that we have a very good understanding of how, as you go back very early into the universe, our models of physics, quantum electrodynamics, quantum electroweak theory, very accurately models how the universe behaves. And yet none of that includes something that we could say, oh, that's what this dark energy is, or the cosmological constant. And so people have been investigating, how do we get a Big Bang model that has this in there in a way that fits with what we know so well? And the way you do that is you say, all right, when you're down below a certain energy, our model accounts for everything really well. There's no place to bring something new in that would cause that. But as you go to higher and higher energies, there are things where we don't know. Our range of what we don't know gets a little bit larger. And so there are contributions that could be made that would say, okay, that would be what the dark energy is. And that's a lot of where the fine-tuning of the dark energy comes in, is that when we say, given where we can see dark energy come into our models, that allows us to say, okay, it comes in at this energy, which means that has consequences for the value of the dark energy we ought to see. And in fact, people recognized this long before we measured the dark energy, and they said, okay, where it would come in is such an incredibly high value. The fact that we don't see it means it's got to be zero. So there's some symmetry that says even though it should come in up here, it cancels it out and you end up with zero. And then back in the 1990s, late 1990s, early 2000s, we find out, lo and behold, no, we actually do have some level of dark energy in our universe. And the problem is where we expected it to be and where we measure it, there's about 120 orders of magnitude between those. And so kind of why I illustrate that is that, a very common way of saying it is, if the dark energy were 1 part in 10 to the 120 larger, we wouldn't have a universe. That's actually not correct, because what's really true is that what we expect and what we measure are separated by 100 orders of or 120 orders of magnitude. We really don't know whether it could be larger or smaller. Could it be larger and you still get life? Could it be smaller and you don't give life? And without that, we really don't know the 1 part in whatever way to say it. But what is definitively true is that what we expect the amount of the energy density and what we measure the energy density are vastly different by these 120 orders of magnitude. And there are some things you could do and say, well, it's really only 60 orders of magnitude. I mean, fine, I'll even grant you that.
That's
the bottom
a lot.
line. Exactly. It's kind of quibbling over bits there, if you will. But one way people have sought to explain that is you say, okay, yes, it is true that what is measured compared to what is expected is vastly different. But that's not the whole picture, because if, for example, let's just say we live in a multiverse where throughout the multiverse, all of the different, or at least the cosmological constant can be larger or smaller. And then you say, all right, what would observers expect to see when they go out and measure it? Now it's not just that, it should be much larger, we measure it much smaller. Now you can ask this question, because there are observers, that's going to limit the value that it could take. And kind of the analogy I would give is, you imagine you're in a lottery winners club. You go around and you ask the first person, hey, you're sitting and talking to them and you find out, but you don't know you're in a lottery winners club. So you go ask the person and you find out, wait a second, this person won the lottery. And they found that out because when you said, hey, I won the lottery, they said, hey, I did too. And then you go get a third person, hey, I won the lottery too. You can count up how the probability of winning the lottery, and you go down there and it's incredibly improbable odds that all of these people won the lottery, except the lottery winners club doesn't exist unless there are lottery winners. And so that analogy applied to our universe or this multiverse is, yes, dark energy in principle could be all over the place. You could have many, many, many people who didn't win the lottery, but the moment you say there's an observer here, that puts a constraint on how the universe has to look, or else the observer can't be there to observe it. And so particularly Steven Weinberg, I think back in the 80s, or 90s, and maybe 2000s, was looking at this and saying, you know what, if we say that, or let's kind of do an analysis, let's just assume that it can vary, the cosmological constant varies throughout the multiverse. What are the values where you get observers? And he did some calculations where he made an assumption that if the amount of or amount of matter in galaxies is proportional to the star formation rate, or how many stars form, and the amount of stars that form is proportional to the amount of life in the universe, then what you can show is that the universes that form the most stars are right around the size of the cosmological constant that we see. And so the idea was, by applying anthropic reasoning, and I use that term specifically because that's the language you used, that if you say, what do humans require, or what do advanced organisms require, by applying that reasoning, that puts a constraint on what sorts of values we're going to see in the universe. Now, the interesting part about that, or what brings this new paper, the new paper is called "The Impact of the Cosmological Constant on Past and Future Star Formation," because what they wanted to do is Steven Weinberg made an assumption that the amount of gas in galaxies is proportional to the amount of stars formed. And it turns out the picture is just more complicated than that, because you could, in universes where the cosmological constant is smaller, you would expect, there's going to be more stars in galaxies, therefore you're going to have more observers below that. Above, as you get a larger cosmological constant, that's going to limit structure formation. So there's going to be this boundary where, once you start getting observers, that is, and then we're going to be kind of right at the edge of where that happens. That was his basic line of reasoning. And it turns out it's just a little more complicated, because what this paper was able to show, they did a more realistic assessment of star formation in a universe with a lower cosmological constant. And not that they did hydrodynamic simulations to get that, because that would be time-consuming to say the least, but they were able to do a more analytic form of that and say, all right, let's reduce the cosmological constant. What they found is that the maximum amount of star formation, the amount of the fraction of matter that became stars, was about 27%. And that happened when the cosmological constant was about 10% of the value that we observe. So the most life-friendly universes in this definition, and life-friendly is the more stars that form, the more life-friendly it is. That actually happens when the cosmological constant is about 10% smaller, 10 times smaller than what we find in our universe. And it is true that the larger it gets, the star formation rate goes down, but it turns out that's a relatively flat decrease. And so you have to get up to quite large values of the cosmological constant before there's significantly small star formation rate. And so they put all of this together, and what they found is that, the conclusions they drew were, one, that our universe is relatively close to the universe that is maximally friendly in terms of the number of stars that are produced. But if you now ask the question, because that's not really the question you want to know, so if we're just saying, what would the observer use? If we were to say, wherever stars are formed, there's some fraction of life, and then you say, we're a representative of that life, what would be the most likely value of the cosmological constant you would measure? And if that were to come up to what we measured, then you say, okay, this is just a consequence of anthropic reasoning, that yes, cosmological constant can vary, but the moment you throw the constraint that life is there, we now measure the value you would expect to see. It turns out that if you say, what is the most likely value you would see, it's about 500 times larger than what we see. So that's a couple orders of magnitude. That's not a trivial change. And so the conclusion they drew from this is that there's got to be something more going on. This is not an adequate explanation for what we would see, because if this were an adequate explanation, the most likely observer sees a cosmological constant that is about 500 times larger than what we see.
Well, a question I've been dying to ask about this paper is, it's not just the number of stars that's crucial for whether or not you get life, especially intelligent life. It's what kinds of stars you get, and what are the relative populations of the small mass stars to big mass stars. That's critical. Did they ever address that in the paper?
Yes and no. So when they came down and said, okay, if we just allow the cosmological constant to vary, the value of the cosmological constant we see doesn't match what the most likely observer would see. So what they say is there's got to be something more going on there. And so they address it in that sense, that there's got to be something more going on. It could be that other constants we see in the universe also vary, and so it's really a combination of those constants. Or and as you're saying, it could very well be it's not just the kind of it's not just the amount of stars you have, it's what kinds of stars do you get.
Well, there's another factor too. Where do the stars form? If they all form in the core of the galaxy, you got a problem.
No, and I think that's what this is saying is I think the hope was when they were doing the paper, they were hoping to say, okay, when we do this analysis with just a few kind of
constraints,
simplistic analysis, few constraints, we're going to say yes, what we see is what we would expect. It's at least, I mean, I would say 500 is in the ballpark. It's not like we're 20 orders of magnitude off here. So it is it is in the ballpark. But we're neither the most life-friendly type of universe in their analysis, which would have a cosmological constant about a factor of 10 smaller, nor are we the most likely measured value, which would be a cosmological constant about 500 times larger. So there's clearly something more going on in there. This in some sense is another way of saying. I think there's more going on to what's going on with the physical constants. But even if you just restrict yourself and say, all right, let's look at the number of stars it formed, there's kind of what I would argue two models of how to look at where you're going to get life. There's the minimalist model, which I would call if you get a star which has a planet that's the right distance away, you're going to get liquid water and you're going to get life. That's kind of where there's liquid water, there's life type model. Scripturally speaking, I don't find that to be the case because you look at Genesis 1. In the beginning, God created the heavens and the earth was formless and void, hostile to life. Darkness was over the surface of the deep, and the Spirit of God was hovering over the surface of the waters. So earth was covered in water, but yet it was still hostile to life. So there's something more going on there. And I would, the rare earth type model, I think I haven't figured out a good name for it. There's the minimalist model, but I would say the maximalist model, that it's not only do you need the right kind of planet around the right kind of star, but it's got to have the right age and the right composition. And there's a lot more that plays into that than where we get liquid water life is. And I think this is a very great place to start because you can only deal with so many.
Well, I think you come up with a good analogy. I mean, you look at the habitable planet question, people saying, hey, liquid water. We now realize there's 14 other habitability requirements for a planet of life. What they're basically saying is not just the population of stars, there's more, because if it was only the population that mattered, we would find a value that would be right at the value we measure for the cosmological, for dark energy. But we don't. It's a little bit off. The fact that it's a little bit off means the population of stars is not the only thing that's important about stars. And we already know.
No, that's true. But it could very well be in this analysis, because I would say this is a good second step in the analysis. But, it's just looking at, does the cosmological constant vary? It could very well be that you also need to deal with the electromagnetic force, so that it varies in there. And we know that there are a lot of aspects of the fundamental laws of physics, the strength of the electromagnetic force, the ratio of that to the strong nuclear force, the electron-proton mass ratio. There's all sorts of things that seem to be fairly, if they were to take values much different than what we see, it seems to be a life-unfriendly universe. And so in some sense, this doesn't surprise me. Just saying, okay, well, the cosmological constant, if we just look at star formation, we're going to solve that. It seems like we already have a lot of things saying there's a lot more to this picture. But I did find this result interesting because when we start to add in more detail about realistic star formation rate, instead of making the result by Weinberg, which was in the ballpark, a good approximation, they go, okay, we just add a little bit more details and it's going to get close. As we added those more details, it actually said, oh, that actually makes the discrepancy a little bit bigger. There's obviously more we need to throw in here.
Right.
And that's very consistent with RTB's message, is that it's not just a couple of things about our universe. It's a lot of stuff about our universe.
Well, for example, we already know it's important when stars form, where stars form, what kinds of stars form, what are the mass ratio distributions. So, and I expect all of that would affect this calculation.
I would expect so too, and you can imagine the more you throw into that calculation, the harder it gets to make.
But it's exciting.
It is, yeah.
The more we study this, the more features of design we discover. So
it really is, and there's another part of me that we'll go back to the discussion about planets that are habitable. And I have to, if I'm candid, I thought, okay, as we starting to find planets that look closer and closer to Earth, and we're not particularly close to Earth now, but we've got a couple of things that, at least in size and distance from the star, in the ballpark, that from an apologetics perspective, if we find a lot of planets that look kind of like Earth, at least superficially, does that make our apologetic case go away or not? And I think, okay, it may hurt it a little bit, but it does also strike me that there's kind of two camps of thinking about things. There's this minimal set of features, and once you get this minimal set of features, you're going to get life. And there's others that say there's a lot that goes into that. Well, you can't just say, well, this is the data, we've got to decide. Until you get more data, there's got to be some way of asking the question, which side has the better position there? And you can't get that data unless you find many more planets that look increasingly close to Earth in some features. And then ultimately, you got to be able to ask the question, can we make a measurement of whether there's life on those? So, I mean, this is, I think 200 years from now, we're still going to be discussing this problem.
But what's happened, Jeff, in the last, 30 years now that we've been discovering these planets outside the solar system, is the more we discover, the more habitability requirements we keep discovering. So we began with just the liquid water habitable zone. And I think the second one that was added was the ultraviolet habitable zone. And we wouldn't have found any of that unless we were actually discovering these exoplanets.
No, that's fair. I think you're right. I think the more I wholeheartedly agree with that. I also think the more data that comes in there, in some sense, the more we get data that allows us to investigate the details, the more the range of positions that people can articulate. Because, okay, I agree. I think there is an ultraviolet habitable zone. But when you look at that, that kind of is related to getting enough energy for the start of life. And again, from a naturalistic scenario. But on the flip side, you go a little bit down into the water and ultraviolet radiation kind of doesn't matter. So, I mean, there's the more details you are, the more flexibility the more possibilities for things to vary in your model, the more chances you have to say, well, it could be this, but that could explain. And so it gets to be this kind of complex picture, but I think that's where a lot of the fun is, actually. So yeah. I'm excited about the developments that have come along.
And what's been fun for me is about every year of new discoveries of exoplanets, we seem to be adding an extra habitability requirement. Mm-hmm. It's roughly we discover an average of one every 2 years. So we're at 15 now out of 30 years. So what's going to happen in the future? And it's amazing we got all this data from just 7,400 exoplanets. So
yes, and like I said, it's a fascinating. To me, I've been able to watch because they actually found the first planet outside our solar system right about the time I started graduate school. So in my scientific career, we've gone from our solar system is the only system where we can measure planets to now there are thousands of stars where we know there are planets. And so it's been fun to watch that growth. And in some sense, it hasn't really muted the controversy is not the right word. The amount of discussion about varying positions there. You got people who think there's life out there, people who don't think there's life out there. It hasn't really muted that. It's just made it a far richer discussion.
Yeah, and a lot of surprises that people were not expecting.
I agree. So
yeah, good.
But
so where's this being published?
This is in the monthly notices of Royal Astronomical Society.
And it's already out?
Yes, it was in November 2024.
Very good.
November 13, 2024.
Right.
So, but as you said here, as you say, the more we know about science, the more we have reasons to believe it. It's fascinating to see how that plays out.
Right.
So. Well, I want to thank you for joining us today on Star Cells and God. I want to encourage you to join the discussion in the comments below. Remember to like this video, subscribe for more content. New episodes come out each Wednesday. They're available here on YouTube and on your favorite podcast app. So be sure to share this video with a friend. Have a great conversation with them about it. And remember, the more we know about science, the more reasons we have to believe.